Alkynes are somewhat acidic. They're weakly acidic. So the hydrogen on this triple bond is weakly acidic. Remember, an acid is something that donates a proton. A proton is a hydrogen ion. So this can act as an acid and donate a hydrogen to this base. It can donate to the NH2 and form ammonia. When it loses this hydrogen ion, then it becomes a negative ion because it has this extra electron, it has a negative charge. It's attracted to the sodium ion, and we get something called a sodium acetylide. But the hydrogen on that double bond can do this. The acidity of a hydrogen atom in an organic compound depends on the hybridization of the carbon. And what we see is that as the hybridization becomes more S-like and less P-like, the acidity of the hydrogen increases. Higher acidity means it's more likely to let its hydrogen go. It's more able to let go of it. The hydrogen on a triply bonded carbon is more acidic than on a double bonded, which is more acidic than a single bonded. This hybridization, it has four single bonds, is sp3. These orbitals are 25% S character and 75% P character. Here we've got 33 1/3% S and 66 2/3% P, sp2. With the triple bond, we have an sp hybrid, which is half S and half P in nature. There's not a picture for that. There ought to be a picture for that.
A question?
Yes?
Does the increasing acidity mean that it's just easier to remove the hydrogen?
Yes. It's easier to remove the hydrogen. Whether it is more likely to undergo a particular reaction or not is going to depend on what the specific mechanism of the reaction is. If we look at, that's not what I wanted to do, and that's not what I wanted to do either. So after it loses the hydrogen ion, it becomes an ion. And so this carbon now, we've talked about carbocations and how carbons don't like to have positive charges. Carbons don't like to have negative charges either. But in this carbon that has the sp orbitals, an sp orbital is shorter and fatter. So so that's an sp orbital. An sp3 orbital is going to be longer. So this is sp, and this is sp3. We'll just go for ends of the spectrum. So this guy has sp3, which this has more p character. It's shaped more like the p orbitals. P orbitals are long and skinny. S orbitals are spherical. This is half s and half p mixed together. And so it's shorter. The electrons are closer to the nucleus. Here we've got this extra electron, and this is more stable because the electrons are closer to the nucleus in this orbital than they are in an sp3 orbital. And so the alkyne is more acidic, more able to let go of a hydrogen ion and become a carboanion. Write an equation for the reaction of 1-hexyne with sodium amide in liquid ammonia. Okay, I do not expect you to know what sodium amide is. Let's just go. That's not what I meant to do. Doing a lot of that today. So this is sodium amide, and this is liquid nitrogen, I'm sorry, liquid ammonia. And so what it does is the NH2 takes the hydrogen from the alkyne, from the carbon-carbon triple bond, and it becomes ammonia, and then this anion pairs up with the sodium. So let's draw that. 1-hexyne would be HC triple bond, C, CH2, CH, 1, 2, 3, 4, 5, 6. Hexyne, triple bond on the first carbon. So liquid ammonia and plus Na plus NH2 minus. This hydrogen on that triple bond is the acidic one. So we're going to end up over here, well, let's just stay with the green. I like green. So that's going to have a lone pair of electrons there and a negative charge. The rest of the molecule doesn't change at all. This hydrogen, this hydrogen comes over here. So we're going to get NH3, which is happier. And this sodium ion is going to come over and balance the charge on this negative ion here. If I gave you a question like this on an exam, I would give you the red stuff. I would give you I'd give you the structure for this, and I'd give you this reagent and that, and then it's a matter of you figuring out, oh, well, what's that going to do? That's hard enough. You don't need to remember what sodium amide is. And I think that's the end. It's the end. Well, the sodium ion was here. And I'm going to write him over here because there's a negative charge here. This is an anion, and we usually write the cation and the anion next to each other because they're attracted to each other.
There's not actually a bond between the sodium and that carbon?
You could say it was an ionic bond, but it's not. There's not a covalent bond, no.